So for item 18, we want to show that A is equal to B if and only if power set of A is equal to the power set of B. So because this is a biconditional, we need to show that A is equal to B implies that power set of A is equal to power set of B, and that power set of A is equal to power set of B implies this. So we're going to do here a two-part proof. And we are going to begin by assuming that A is equal to B and show that it leads to power set of A is equal to power set of B. So, and just one quick note, to show that power set of A is equal to power set of B, I need to show double inclusion. So what I want here is to eventually get to the point where power set of A is a subset of power set of B, and the power set of B is a subset of the power set of A. So the power set of A is equal to the power set of B. So this is my my ultimate goal, right, to show a double inclusion, which means that they are going to be the same. So I'm just going to leave it here just to orient my decision making in my proof. And this is something that I recommend doing. Just kind of put where you want to end up and try to develop from there. So I'm going to say part one, let A equal to B. Well, if A is equal to B, then by definition, it means that A is a subset of B and B is a subset of A, right? So what I'm going to do here is I'm going to produce some object in the power set of A and show that it must be inside the power set of B and vice versa. So I'm going to say let X belong to the power set of A, right? We're just saying that. So if X belongs to the power set of A, by definition, it means that X is a subset of A, right? That's what it means for it to be in the power set. And then we're going to have that note that A is a subset of B. So if X is contained in A, if X is a subset of A and A is a subset of B, then X is a subset of B. So if X is a subset of B, then by definition, it belongs in the power set of B, right? So we have that X being a subset of B implies that X belongs to the power set of B. So if X belongs to PA implies that X belongs to the power set of B, so the power set of A is a subset of the power set of B. So we've shown one of the inclusions, and now we want to show the other way. So we're going to do the same thing. I'm going to say let W belong to the power set of B. So if W belongs to the power set of B, then by definition, as I've written before, it means that W is a subset of B, right? That's what it means for it to be an element of the power set of B. So we have that W is contained in B and B is contained in A, so it means that W is a subset of A. So if W is a subset of A, thus it means that then W belongs in the power set of A, right? That's the definition of the power set. The power set contains all the subsets. So if W is a subset of A, it's definitely in the power set. So what we have here is that W belonging to the power set of B implies W belongs to the power set of A, so power set of B is a subset of the power set of A. So I've shown here a double inclusion, right? Because over here, I've shown that the power set of A is a subset of the power set of B, and over here, I've concluded that the power set of B is a subset of the power set of A. And so when we have this double inclusion, it means by definition that power set of A is equal to power set of B. So that is it for part one. We've shown that A is equal to B implies that power set of A is equal to the power set of B. And now we're going to work backwards. So we're going to say part two let power set of A be equal to the power set of B. And so similarly, what I'm looking for is a double inclusion. I'm looking for A is a subset of B and B is a subset of A, so A is equal to B. So this is what I ultimately want. And let me just move it a little bit lower so that we have space to work. Okay, so we're saying let power set of A be equal to the power set of B. Right, so if this is true, then by definition, then power set of A is a subset of the power set of B, and the power set of B is a subset of the power set of A. And then we're going to say, note that A is a subset of A, because every set is a subset of itself, right? So if A is a subset of A, then by definition, this means that A belongs to the power set of A, right? If A is a subset of A, then A definitely belongs in that power set. And then we say we have that PA is equal to PB. So A belongs to the power set B, right? And what does this mean? What does this mean here? A belonging to PA implies that A belongs to the power set of B, so the power set of so A belongs to PB. Wait, I think I took A. Oh wait, yeah, there's one thing here. So A belongs to the power set of B. Well, if A belongs to the power set of B, it means that A is a subset of B, right? That's what it means for it to belong to the power set of B. So A belongs to the power set of B implies that A is a subset of B, because that's the definition, right? If it's in the power set of B, that means that it is a subset of B. So we've shown one of the inclusions, and the other inclusion that we want to show, we're going to say, note that B is a subset of B. So if B is a subset of B, then B is inside the power set of B, right? That's just the definition. We have that PA is equal to the power set of B. So if B is inside the power set of B, it means that B is inside of the power set of A, which in turn, if B is an element of the power set of A, it implies that B is a subset of A. Right? This is what it implies. So we have shown here that A is a subset of B and that B is a subset of A. So we have shown double inclusion. Therefore, A is a subset of B and B is a subset of A, so A is equal to B. And that is it. We have shown both parts. So let me just scroll down. So here's part 1. That is part 2. And so our conclusion is going to be that A equals to B if and only if PA is equal to PB. And that is it for this question.